Today we will going to talk about a lot of things and who we are. We are Dempaflux. We are a new method of providing EMC solution to modern electronics companies. And one way we always believe is that EMC expertise and EMC topics are not so much available in the market. So we try to bring experts, guys like Francesco. They are so renowned in industry. So we always try to bring and put it in front of you guys. So today we are here for master EMC design process. And I want to give you a bit of background about Francesco Poderico. He has spent more than 25 years in electronics field, and as I am aware, I know Francesco from last 2 years now. He's one of the amazing guys in the field, and he always comes up with new ideas and plan, and he always try to share his things. He has all the knowledge that includes electronic design, firmware development, PCB layout engineering. Not only that, he's also been amazing in helping companies overcome failed EMC challenges. And today, Francesco will share some of the templates or some of the patterns he saw and how we can resolve it. So, thank you, Francesco, for joining our session. I'm really excited. And you can now, share your screen and we can start the session.
Okay, good morning, everybody. Can you see the screen, guys?
Yeah.
Excellent. Okay. Okay. The first things that we need to understand is why we are failing EMC, why we are failing EMC. And there are several reasons, but the most important is a very, very difficult subject. Okay. EMC, to design electronic that pass EMC, you need to be an expert of signal integrity, power integrity, and there are things that you may have a design that is perfect, and then you use, for example, metallic enclosure. You don't connect the enclosure to any part of your PCB. You may have the enclosure, for example, works as antenna, and you have other effects. So it's a very, very, very difficult effect, very, very difficult subject. And you also, depending from the test that you are doing, there are usually different kind of emission path. Some emission path for very low frequency, below 30 megahertz, and there are different emission path for frequency goes above 30 to 80 megahertz. So the subject can be quite difficult. Okay. And so over my career, I started to create a process that minimize the risk of failure. Okay, and I'm going to share this with you. So the designing process that when you're designing a new product, okay, you need to put EMC. The EMC design needs to be inside your design from the beginning. Okay, so don't start the design until you know very well which EMC standard to apply, and I will say even which safety standard to apply. Okay. Then over the year, because I've done this for so many years, I got my own template, and I'm going to share as much as possible today in the limited time that we have with you. Okay. Some of this template, uh, I probably I can say that almost 100% of the design I made, I pass at the first time EMC. So the templates that some of the templates that I'm going to share with you are very basic, but I think it gives you an idea of what kind of mindset you need to have in order to pass EMC. Okay. So a design phase is an phase. So in the first phase, you, as I said, the design not started yet, understand the stamp, and then start using your template. So if you are a design consultant like me, usually you have a customer that came to me and ask, Francesco, I want a design with X, Y, Z, for this market and so on. If you work for a corporation, you're going to have a functional spec, for example, from the marketing guy or from the salesman or from your boss. And before you actually start your design, you need to ask a question like, what is the application? Medical, for example, is this a medical product or is this a light industrial, heavy industrial, automotive, and so on, military, so on. So this the end application has got a very massive effect on the kind of design of the way you design your electronic. Just to make you an example, if you are designing something for the automotive, some of the tests for the automotive, the video immunity, for example, your electronics has got a field up to 80 volt per meter. 80 volt per meter is a lot. It's a real lot. And if you some of this template, for example, works for very well for automotive industry. For instance, and imagine, for example, this is very important. Imagine, for example, you design a braking system, an electronic braking system, and imagine that, for example, it's very weak on the reading immunity. You may have the car stops in the wrong time. Okay, so this kind of design are extremely, the template I'm going to share is extremely important to make sure that your system is immune from reading immunity, conductive immunity, and other things. Medical, for example, is another extremely difficult, design is from medical is very difficult, not just from the EMC, but probably from safety. But automotive, in terms of immunity, is probably one of the most difficult. Okay, so the first question you need to ask is the application. Then, when you know what you have to design, you need to have an overview of the system. For example, if you have a box, if you design something that has got a lot of cable, on this cable you may or may not have some testing. For example, if you have, just make some example, if you're designing something that control the light of a building, and you have, for example, your control line that goes in parallel to the main line, there are some quite severe tests, for example, you have to do on this cable, because usually this cable are longer than 10 meter or longer than 10 meter. Yes, you need to do some tests like surge, and so that could be demanding, for example. So a question you need to ask is, if you have some cable, how long are this cable and where they connect to? Okay, and checking with the standard, that try to understand if you need to do some specific test on this cable. Typical tests are surge, fast balancing. Okay. Of course, you have even other tests you have to do, like conductive emission, but usually the most severe is the surge. Okay. Then you need to ask questions like, how is powered? AC, DC, USB, power Ethernet. Okay. And depending if you are selling or not the power supply, you may or may not to do some tests. For example, imagine you have a product like, I don't know, you are designing a phone and you're selling the phone without the USB. If you are selling the phone without USB charger, you need to do a test, conductive emission test on the USB cable. But if you sell the phone with a charger, and in the instruction says you must use all this charger, then the conductive emission needs to be done at the AC line. So this kind of questions are very important because you may or may not design some filtering depending the system you sell. Okay. Another important question you need to ask is the enclosure. Usually there are kind of the choice today that pretty much two is usually a plastic or metal. When the enclosure is a plastic, in my opinion, somehow is pretty easy sometimes, because the metal sometimes, if you cannot connect to the metal to any point of your board, sometimes you have a problem. But I'm not going to discuss this. It is quite counterintuitive, but sometimes you have a problem. Then, if you are selling the unit with, for example, some radio transmitter, so for example, I imagine most of you know what is an ESP32, for example. You need to ask a question like if this transmitter that you are using comes with RED certification. RED certification is Radio Emitter Device certification. If you have Bluetooth, you need to know if you have to pay the listening for the Bluetooth, and so on. So everything is added. You need to do some check that you don't want to arrive to the end of the design and then discover, for example, that you have to spend another 40,000 pounds for another certification, for example. So all these questions need to start at the beginning. Last question that is extremely important: in which country you are going to serve. Okay. EMC standard change from country to country. There is some kind of we are trying to harmonize the standard, but they're not quite the same. So, for example, if you're selling Europe and in America, for example, America, North America, usually as long as you do CE and FCC, you're okay. If you start to serve another country, South Korea, for example, South Korea, for example, does not accept if you have a radio transmitter. South Korea does not accept a test done in this part of the world. The radio emission needs to be done in South Korea. So every country has got their own rules, and you need to know this before you start the design. Otherwise, you end up with a big problem. Once you know which standard to apply, you can start to once you know which part to apply, which part to apply, you need to use some template. In my case, I'm going to share my template that you can start to use on your electronics. For example, power cable. Usually, I know that there are some tests like conductive emission, radiated emission, conductive emission, conductive immunity, surge, fast transient, and so on. So you apply a topology of solution for the power cable, for the AC cable, for digital input, digital output. Hence, the bigger is this template that you have, the less likely is that you are going to fail. Okay. Now I have a lot of experience in designing. Only this year, guys, just to give you an idea, I designed 2 boards, and it's only February. And so, so the more experience you have, the larger is this let's call database of templates that you have. Okay, so I'm going to share some with you today. Okay, the one that I have seen, the most common that you need, because everybody's got some DC power, everybody's got some AC power. But I also am going to share some that you will not find written in any book. Okay, and the one that I'm going to share that you won't find written in any book is applicable for standard like automotive, for example. So let's start with typical template that I've got for DC power. Yeah. Okay, for DC power. This is a typical template that if you follow this kind of topology, you're not going to fail. Okay. Now, you need to ignore the value that I've got here, the kind of use, and look just the topology for now. From the left, we have you see the mouse, guys. You see the mouse.
No.
If I move a mouse, no, okay.
Yeah, now I can. Yeah, Francesco, it's visible now.
Is it visible? The mouse? Not visible. No. Okay. Okay. J1 from the left you can see an input connector, and on the right, in this particular template, you see electronics, our electronics. For example, this is converter. No. And this is the topology that I use in most of my design. And I'm going to explain components by components, the functionality of all this. Now, before you start over design, you don't know if you need this. You don't know. You don't know if you need a C1, C9, FB2, FB1, C2, C10. You don't know if you need this. So usually what I do, I design with everything. I mean it. When I do the EMC test, I don't fit everything. I fit only what I believe is the minimum. Okay, because the more components you put, the more expensive is the design. However, when you do tests like conductive emission, for example, and if you don't have, for example, a common mode choke, you are failing, you need to redesign the board. Something that instead I recommend is put everything you need, don't fit, do the EMC test. If you fail, then you start to populate. So I'm going to be to go in details on every part of this particular template. Okay. The first part I'm going to discuss is the fuse, positional fuse of and this TVS. Okay, a TVS, I'm pretty sure everybody will know what is it. It's a component that adjusts the voltage within limits. Okay, there are usually several kinds of TVS. There are the most common are varistors. Varistors is a TVS that is designed to absorb a very large power. Okay, so for example, if this will go to I don't know within if you're expecting here to have a surge test, you should use a varistor, not a TVS. Okay. For example, if this is powering something that is inside a car, the surge test is quite demanding there. In the program varistor, not a TVS. Instead, if you are not expecting surge, if you're expecting only ESD testing or fast transient, usually a TVS, for TVS, I mean a silicon TVS, is usually best choice. Okay. Also, keep in mind, guys, that the varistor over the time, the voltage, the chopping voltage of a varistor reduce. For example, if you have a varistor that is 40 volt, just cut at 40 volt, after 10 years, you need to imagine that you need to take in consideration that after 10 years, probably start to cut at 10 volt. Because the varistor, the way it works, every time it works as a varistor, the chopping voltage decrease. And so you need to, during the design phase, you need to decide this at the beginning. The fuse, look at the position of the fuse. When you're applying a surge here, the fuse, if it's the wrong fuse, it will get damaged. Okay, so usually the fuse that you must use these days, they are called anti-surge fuse or slow blow fuse. Okay, so it's a fuse designed to survive a test like fast transient surge. Okay, and the position is just before the TVS. Okay, so this is the few things that you should put in every this input. Of course, the fuse and the TVS, and in this particular order. Then, when you do one typical test that you do on a cable is you need to know a cable when you do a test in a cable in a EMC house, usually they ask you to use a cable that is between 2 to 2.5 meters. That can be short, but usually it's a couple of meters. And sometimes cable works like antenna. Okay, works like antenna, and in the range of between 150 to 200 megahertz, they can emit. Okay. Sometimes the frequency range is lower, but usually this is the frequency range. So to minimize the emission of your cable, usually what you can do, you can use a ferrite and a capacitor that on every line, imagine this is a positive, and the one SB1 C1 is a low pass filter for the emission, same as FB2 C9 is a low pass filter for the emission, and both the positive and negative of your cable needs to be filtered in this way. FB1 C2, same as FB2 C10, instead they works like the other way around. As I said, the cable is antenna, and when you do a test like a radiated muting, some RF may come into your antenna, and pretty much, you really don't want that. Okay. Then another things I do is I add common mode choke. Common mode choke L1 is you can see in this template I've got 2 ohm resistor in parallel to the common mode choke. In reality, you hope you don't need, and you fit the EMC during the EMC test. I fit the 0 ohm resistor. However, if I got some problem, I remove R1, I remove R2, and I've got already in place the common mode filter. I selected the common mode filter always to give me below 30 megahertz, something like 20 30 dB attenuation, and I use tools like Red Expert to evaluate this. Usually with 20 30 dB attenuation, you're usually okay. And so imagine I do the EMC testing with R1, L, R2 fitted. I fail, I remove R1, remove R2, and I try again. Okay. Then in parallel to the input, usually I use 2 kinds of capacitor, electrolytic and ceramic. When you need to know, guys, that when electrolytic capacitor, they are usually much bigger than ceramic, but they works well. Let's say up to 100 kilohertz. Okay. Instead, ceramic capacitor, they works well above this frequency, but they usually the value of this capacitor usually is much smaller than electrolytic. So the reason why you need electrolytic and capacitor and ceramic in parallel is to have a wider band as possible. You try to have a DC that works as a DC in the widest spectrum as possible. And this electric capacitor, they're extremely important because when that value is too low, you're going to have oscillation on the cable, guaranteed. Sometimes I fix this kind of emission on the cable just by adding more capacitor. Yeah. Okay. So don't forget, a typical mistake I was saying, bulk capacitor too small. Okay, so try to have a capacitor that are not too small. Okay. So this kind of topology, usually improve radiated emission, conductive emission, also radiated immunity, conductive immunity. And finally, on this area C6, C7, C8, a lot of time on this on the DC of the input side of your electronic, there is a DC converter, which is very noisy, and he requires bulk capacitor, very big capacitor, C6, but he also requires ceramic capacitance like 100 nanofarad. Today you can find ceramic 10 microfarad as well on this side. So coming back on this circuit, you can see that every component that we got here, they got a functionality, a specific functionality. What I call the D1 here is for surge and fast transient. What I call the C1 and the FB1 here is for improving radiated immunity emission at above 30 megahertz. C2 and the FB1 improve radiated immunity instead at high frequency. L1, C6, C5, C4, C7 improve conductive emission and conductive immunity. So every one of these has got a specific functionality. Okay. And so I'm not suggesting you guys to fit everything, but design in a way that there is space. You can add this capacitor if you have some problem. Okay. I'm saying that because your customer, your boss, your customer will always ask you to reduce the cost. At the same time, you won't even minimize the chance to fail. Okay, and this is for my template for DC power. This is my template. For this is within that template you are protected from over voltage, fast transient, surge. Another thing I forgot to say, when you apply a DC voltage here, because you got some, you have some ceramic capacitance. Sometimes on the instant you plug your DC, you have another voltage. So a key guess is to help you to protect your electronic from every time you plug a new DC. So coming back here, so we saw that we have some common mode choke and some capacitor that improve your emission between 150 kilohertz per megahertz. We saw how the emission and the immunity has improved even above 30 megahertz. And we know that choosing the right fuse, the fuse will never get damaged as long as it's an anti-surge fuse. Okay. AC line. Okay, the template that I had before is the template that I use for DC. Now this is a template for AC. Okay, AC you need to be more careful than DC because you cannot choose any component you like. For example, imagine you have light, neutral, and the earth, for example, and you are trying to use the same topology that I used before. For example, common mode choke with this C1 to improve the emission at low frequency. This capacitor C11, C15, their capacitor they call the Y capacitor. Okay. Y capacitor is a capacitor that when gets damaged, will not get damaged at a short. For example, imagine a ceramic capacitor, when they get damaged, usually they get shorted. But Y capacitor, they use a technology such that when they get damaged for any reason, they're open. They're always open. Okay. Because you really don't want any car, you don't want, for example, that your light is shorted to earth. Imagine you are in a building and for some reason light is shorted to earth. You put I risk the life of everybody in that building because on the earth you have the light thing. So while the topology, what I'm trying to say, while the topology is very similar to the topology of this thing, choosing the right kind of capacitor is important. So, for example, in this particular design, I'm using still a fuse as before, an anti-surge fuse, because I know that between live and neutral, we are going to do a lot of surge tests, and surge tests are very, very demanding. This time I have used the symbol that usually I use for varistor, because the energy you use between live and neutral is usually much higher. And you need a varistor that survive this. Then there is you can see here a capacitor which I wrote X1. Same reason as the capacitor that I called here C11 This capacitor, they need to meet a specific standard. So they are usually called X capacitor. And depending on the application, sometimes you have to use the X1 or X2, same for the Y capacitor. You need to check the standard. In this example, I put X1 because I use pretty much all the X1 and Y capacitor in my design to be safe. Okay, coming back on this kind of topology, this varistor is going to protect you from surge capacitance. Okay, the surge capacitance is done in every phase, done between live and neutral, but it is also done between live air and neutral air. So you also need, if you're using earth in your design, you also need varistors in this location and this location. And this is the reason why I got RV1, RV2, RV3. If you cannot use earth, of course you don't have RV1, C11, RV3, C15. Okay. Then we have a common mode choke. I need to say when you use AC, you do need this kind of topology. It's very unlikely that you don't need a common mode choke. Very, very unlikely. Because at some point in the location where I write live F, neutral F, F is for filter, usually you have an AC to DC converter. And usually this power supply are quite noisy. And you really need a common mode choke. Okay, and I do the same pretty much. I select a common mode choke that it gives me between 20 and 30 dB below 30 megahertz. Okay, so you can use tools like Red Expert to do a simulation, and there with Red Expert you can I think they're assuming that it impedance here, which is the impedance of a listen. So it's pretty much okay. So here I'm going details. I was expecting explaining exactly what I was doing. The fuse is, as I said, is anti-surge fuse, and RV1, RV2, RV3 protecting from a surge test in the past transient, and C11, C15, C13 improve your emission, the low frequency. And instead, C12, CM1, C16, C14, they improve instead the immunity, but immunity. Okay. Most of the time, in most of my design, most of the time I don't use the C12, C14, C15. Most of the time I'm more interested in this emission. I never had a problem with immunity. But when you buy one of these filter pre-made, most of the time they don't have C11, C2. They're designed to improve the immunity more than emission. So it depends where you're worried. If you're worried to have a problem during the immunity, C12, C16 is a good idea. But if you are worried for the emission, you need C11 and C15. Okay. Now I'm going to go to discuss some other tips and tricks that came pretty much from my experience. Okay, this one is something you probably never saw. You won't find this written in any book, and I think this is pretty much my own solution. When you are designing something for example, automotive industry, for example, well, you need to have a very strong immunity with both on radiated immunity and conductive immunity. Usually, one of the tests you have, for example, you're sending an 1 kilohertz modulated signal, usually with an 80% of modulation index, of a very large frequency range. So you have usually from 30 megahertz up to 1 giga, for example, or more now, depends on the standard. Sometimes this 1 kilohertz sine wave, when it goes to the especially positive input of an operational amplifier, gets demodulated. And as a result, you have a 1 kilohertz at the output of your operational amplifier. Okay. So you need to imagine at the input of your operational amplifier, you have somehow an AM modulated 1 kilohertz signal that gets demodulated. And the demodulation, most of the time, as I said, happens to the positive input of operational amplifier. And you have a sine wave here. What do I do? What I do is I connect a capacitor between the positive and negative of your operational amplifier. Okay. Now, this capacitance, if it's too high, is going to make your operational amplifier very unstable. So this capacitance needs to be small as possible. Typical value, they go from a few picofarad to 1 nanofarad, no more than that. Okay. In pretty much in all my design, I've got capacitor which I don't fit, but it's there in case I've got this particular failure during the EMC testing. So in my suggestion, every time you go to an operational amplifier, two things. First, choose an operational amplifier with the bandwidth smallest possible. Okay. You don't want a 100 megahertz bandwidth operational amplifier if you are sampling, for example, at 1 kilohertz. No. Why you want an amplifier with such a bigger bandwidth? So choose an operational amplifier with a very small bandwidth, plus put space between the negative input, the positive input for capacitance. And if during the test you have here a sine wave or you are failing, fit this capacitance. Now, there is a trick that I'm going to share with you to understand if you need to fit this capacitor or not. If during a test, let's say you're failing at 300 megahertz, 300 megahertz, your equipment does not work, ask the EMC house to remove the demodulated signal. Demodulated signal. Ask them to do the same test, same frequency, but remove the 1 kilohertz demodulation signal. If you are still failing, means the capacitor will not solve the problem. If you are passing, it means that is the 1 kilohertz is demodulated somewhere. Okay. In that case, this capacitor may have. This kind of trick works even on diodes. Sometimes, imagine you have a diode. Sometimes you have to put a capacitor in parallel to diode to stop this kind of unwanted demodulation. So this is as I said, you won't find this written in any book. This is something that I recommend you to do in your design. This one is another one. When you have a clock that goes to one or more memory. Okay. Basically, sometimes what may happen, is that this clock may meet. Okay, because the screw is wide. The reason why you may fail because imagine you have a clock and you have a track. There's nothing on the other side. Of course, you're going to have some emission. And you have this. In my experience, you have this particular problem on all three lines: clock, RAS, and CAS. Imagine you have an SD lamp. You have usually this problem on these three particular lines. So you don't have the problem on the data, because a lot of time on data you have usually people put 22 ohm resistor, but on these three particular lines, people usually they don't fit anything. So I got a solution. I use a template. On the clock side, I use a capacitor which I don't fit, but is there if I got problem. And the resistor, which I use 0 ohm, but is there if I got some problem. Now, if during the emission I got, for example, I find out that I got a lot of, let's imagine this block is 10 megahertz, and I got a lot of problem at 30 megahertz, 50 megahertz, 70 megahertz, third order harmonic. It means that this my clock is too sharp. It's too sharp, and usually by adding a few picofarad capacitor here, I may reduce the edge just enough to reduce the third order harmonic. So what I'm saying is, I still want a very sharp edge, a very sharp square wave, but I don't want a square wave that is very sharp, which is going to give me the third order harmonic. So this capacitor, a lot of the time, has helped me to improve emission of third order harmonic. Instead, if I got the second order harmonic, which means the line is completely unmatched, by adding a small resistor, okay. By the way, guys, the resistor has got effect even on third order harmonic, but usually the resistor is going to improve the emission on the second order harmonic. Okay, and usually it's between 5 to 100 ohm, and only I think last year a friend of mine contacted me. He had problem actually on a memory. I recommend him this kind of topology, and thanks for this resistor, he managed to pass the test. Actually, I did this more than one design this year, last year. So this is I hope these two I think guys are quite intensive. I hope I managed to pass you what what I was trying to. Okay. When you have a two-phase or three-phase system, I usually use varistor everywhere. Yes. And this is a typical solution that I use. This is another of my template, pretty much. I use pretty much this template in most of my design. Motors. When you have a DC motor, guys, whenever DC motor, sometimes not just DC motor, but even brushless motor, sometimes you have emission at the motor side. Okay. And the simplest way to fix usually is to add some capacitor between positive and negative. And when this doesn't work, if you see, I have added even some wire capacitor between positive, negative, and earth. Sometimes you can do, sometimes you can't. I decided to put this in this particular slide because I had occasion where the unit had some earth, and the only way to fix was to put a capacitor between positive and earth and negative in the earth. Remember always that for safety reasons on this capacitor, usually they must be Y capacitor. Okay. Here was X because for that particular application, the voltage was such that it was supposed to be X. But usually keep in mind that check the standard. But if you're connecting positive, negative, sometimes you must use Y capacitor. Okay. Also because sometimes you have to do when I found isolation test in Earth and your design. So it depends. So I wrote here they may need to be X, Y, but you need to check your standard. Okay. Another template. This is something that I used to do pretty much in all my design. It's a bit difficult. I hope I will manage to pass you what I'm trying to say. When you have a connector, imagine, for example, we have something. In this particular template, where I write the signal in is a connector, and when I write, let's say, PCD is my PCD. I use this kind of topology where I got a capacitor, upper right, another capacitor. And what I do is the first, sometimes you don't know in which frequency range you are going to pair, if you are going to pair. There's a good idea to have a component that can be either a resistor, can be an inductance, or can be a ferrite, which can be fitted if you are going to pair when you're doing either radiating unity or conducting unity on that particular cable. So now every connector, I try to protect every single digital input or analog input in a very wide frequency range. And I do this by adding I do not fit varistor or I do not fit ferrite, inductance or resistance, and some do not fit capacitance. If during the test I fail, I fit them. You may notice that there are two different symbols here. One, you can see a kind of F symbol, another one 0 volt symbol. These two, let's call 0 volt, they are connected together in one point. And I do this. So I cannot, today I cannot show you the layout, but I do this to improve ESD. In reality, if you create around the connector a kind of guard, you minimize the chance that when you're ESD, your voltage goes everywhere in your board in an uncontrolled way. Usually, so the reason why these two symbols are different is because at layout level, even if these two are connected in one point, in reality, they're connected in a way that an ESD high voltage point, we not go to the board. But today we don't have time to discuss that. Sorry. But I want to share with you this kind of topology. Another things that I'm recommend you to do, guys, is this. Sometimes you need to do fast transient on cable. And the positive pin of sometimes of an operation amplifier is connected through your input. Now imagine you need to do fast transient where from a connector and you have a varistor. Even if you have a varistor, you may have a very large voltage at the input of your operation amplifier. So to solve this, usually I add a resistance to limit the current, together with, for example, some diode. So, and the idea is that I don't want the voltage on 0.5 to go too high. I want the voltage on 0.5 to be as small as possible. Okay, because without this, operation amplifier will not survive to, for example, switch. Now, the standard, for example, there are industries like light industry, where you have sometimes wires that are they go they're wired very close to the main. In that particular industry, you need to do field test on this kind of connector. So without this solution, this kind of solution, resistor with this, your operation amplifier will get damaged. And then the last one, typical mistake, when you have a heat sink, guys, heat sink, they works like antenna, like patch antenna. So in your design, every time you have a heat sink, try to connect, if you can, the heat sink to your okay. How you connect does not matter. You can connect with zero resistor, you can connect with capacitor, inductance. Usually, it really does not matter. But what is important is that the heat sink is not isolated from your ground. Because when it's completely isolated from the ground, the heat sink works like a patch antenna and it's going to emit. Same I can say with when your electronics is in a metallic enclosure, completely isolated. It works like a patch antenna, and this is very counterintuitive. I don't want to discuss this today, but what I'm trying to say, every time you have any metal, not connected to your board, this piece of metal, doesn't matter how big or small it is, it may work like antenna. So try to connect the metal to your board if you can. So yeah, I think for now it's all. Now I don't know. Yeah, it's 10. Yeah, just 5 minutes left.
Yeah.
I think yeah, just in time.
Thank you.
I hope that you like
Thank you, Francesco, for sharing it. I feel like that was quite an insightful because some of the application even I wasn't aware that you can use, IO filtering like that. So this was really, really insightful. I think you don't usually find such things until you have worked on multiple, projects and also EMC challenges. And talking about EMC challenges, Dempaflux is a startup based in Munich, Germany. And what we are trying to build is we learned a lot of EMC challenges arises from hit and trial. And as an hardware engineer, you always lack EMC resources or expertise. Apple companies like Apple's also, go through challenges that even they cannot control certain radiation emission. So having such a big budget like Apple's have such challenges, I can imagine how small to medium scale companies handling EMC solutions. So what we're trying to build is we are trying to build one of the first kind EMC solution where we are trying to provide 360 solutions for EMC services. And here you will see that you go on our website, you can create your free account. You will have a preloaded file in your account. And once you create an account, you will see on left side listed of projects. Basically, these are demo projects. These projects showcase that if you are working on a project and you will be, for example, working with Dempaflux, how it will look like. So for example, there is this MSP 430 board. You can see it's an IoT project. They are working for EU certification, CE conformity, and you can add your project description. So what happens is you can upload any kind of design data. Is it a PCB design, schematic design? Even if you're trying to find an EMC standardization, we can also help you there. So once you upload your design file, our algorithm and EMC experts work on that. And then you will see a beautiful EMC visualizer, and it highlights all the critical EMC issues on your board. And not only that, once you click one of the board on the left side, you will see all the categories, what kind of detections you have. And once you click on one of the category, on the right side, you will have a detection. So we provide a reasoning why this is happening. And also we provide a recommendation how to solve it. So we are not only working on PCB designs, but I can give you another example of Antila board. And this is basically a very flexible controller for IoT project. Even on schematic diagrams, if you have a schematic file, you can also upload that. We also do an analysis reviews part, and then once your project is good to go without EMC issues, then we also give you certain health score. That is your board at risk, is it healthy, and what needs to be done. And in this manner you can easily see, like, this is an example of schematics which has been uploaded, and then we highlight where the issue is happening. We give you a provided category, and then a detection, what is the reason behind it, and a recommendation. So this is how Dempaflex works. And even if those recommendations are not enough, EMC experts like Francesco, Ignacio, you can always connect with them. We always provide EMC expert calls. So once the report is ready, you can book a call and you can talk about your other EMC challenges. So that's how we work. And this is what Dempaflux is. Francesco, let's move on to the Q&A. I know we are already a bit late, but yeah, we can jump on certain questions because there are lots of them. We can give 5-10 minutes for the audience. And Francesco, if you are still here, the first question is from Amba Prasad. What is your recommendation on chassis ground? Application is telecom.
Chassis ground telecom.
Yeah.
Well, it's very generic. So
Okay.
it depends on it really depends. It really depends on the system. Application a solution. A solution usually may work in a particular. It's important to know how a system is connected to everything else. Okay, and without knowing this, usually very difficult for me to make a suggestion.
Sure,
What
Francesco.
you need to try, what I try to do usually, it's usually possible to connect the chassis at a high frequency to somehow to your PCB, for example, with a wire capacitor. If you can do this, it's usually it's a good idea to have the possibility to. Okay, so what you can do in your design, for example, having the possibility to have a wire capacitor. Again, this depends from application to application. It's not always possible, but if it's possible, try to remember that if you have a metal, it's completely unshielded, so it's completely unconnected to your equipment. This piece of metal, it may go against you and works like a touch antenna. So try to connect somehow with some impedance together.
Okay, thank you, Francesco. Next question is from Fabriante. I think the question was related to first slide where we were talking about why EMC fails. And the question is, what's the fundamental reason RF behavior change at exact 30 megahertz? Was there particular?
Usually you do two different kind of tests. For conductor emission, you do, for example, 150 kilohertz to 30 megahertz, and then you do a different test from 30 megahertz to above, at least 1 gigahertz. And the test setup is different. Okay, because of this difference in the test setup, the emission path is different. Now, maybe we can discuss this in the future, but for now, I can tell you that because of the setup is different, you have two different paths of emission.
Okay, thank you. Next question is from Marco. On the DC power supply template, does ground mean on the PCB or on the housing if metallic?
That particular symbol was the PCB.
PCB. Okay, so it was on PCB. Next question is from Tanya. Which capacitors are for emission and which are for immunity at the AC line design?
Yeah, if you guys take the slide, can they download the slide?
Francesco, yes, we will be sharing slides with the audience.
Yes.
Yeah.
there are slides where I wrote which one are for emission and which one are for emission.
Okay, thank you.
So if you download the slide, you should be able to have an idea. Usually, the emission, if you see LC filter, okay, you need to, that is a typical topology of LC filter. So if you remember, if you see that as a LC filter, it should be obvious for you guys to understand which one is for what.
Okay, thank you, Francesco. Next question is from Martin. Why do you put the capacitor before the resistor?
Okay. When you have a clock driver, you need to imagine the clock driver has got some resistor. So in reality, what you have an internal resistor. Imagine a clock driver has got an internal resistor of 10 ohm. So you need to imagine you have a 10 ohm of the clock driver, then you have a capacitor, then another resistor. Now, if you put the capacitor after the second resistor, you have an RC filter very strong. Okay, so and the clock does not look like a clock. It looks like a kind of a low pass filter, kind of RC, which you don't want. You really want that the clock is as sharp as possible. Okay, so you put the capacitor a little bit before that resistor, because you are trying to smooth just the edge, the edge of the sharpness. So imagine you don't have a clock of this, you have a clock, but just at the edge, just like that. You want to remove just the third order harmonic, guys. Yeah. Instead, the resistor is to the resistor usually they improves everything, third and second order harmonic. But usually, if you have a resistor, when you have the resistor, definitely you have some reflection. Okay. And so the functionality is that you should not really see like another filter, but you need to see like something we are changing the way we are changing, we are tuning the second and third order harmonic. You need to see this from a frequency domain more than.
Yeah, I think the next one I can answer from Amin. Does Dempa Flux suggestions cover EMI filter stage as well? Yes, it does. We have different kind of categories and detections which we cover. It all depends on PCB rules and also the algorithm. But yeah, we cover all kind of EMI filter stage. I think one more we can go. How does the PCB ground is connected if the enclosure is plastic?
Again, depending from application to application, I cannot give you a straight answer. And
Yes,
depends if what kind of test you have to do.
that's right. I think one last question and then we can go, Francesco. The question is from Tanya. How do you calculate the design of DC power supply? Well, and yeah, attenuate cable emission in the range of 150 kilohertz to 3 megahertz.
Usually, many times I try to put all 30 dB attenuation with frequency range. Okay, there are tools like red tools and experience as well, where I know that by adding a particular filter, I try to get 30 dB. I try to, guys, my suggestion is you can use even actually LT spice to have this kind of to do this kind of calculation. I think some time ago if you I did wrote in the past an application on how to use LT spice to improve conductive immunity, conductive emission. Sorry. So if you Google my name, you should be able to find that particular article. And in that article, you will find how actually to simulate that.
Okay, thank you, Francesco. I think that will be all for today. Thank you, everyone, for joining.